Hello everyone, Human Hard Drive here. Today on A Breadboard, we're going to be talking about RC filters. Now, I did an Electronics 101 video on this, but on A Breadboard, on A Breadboard, on A Breadboard, we're going to be looking a little more in depth as to how they work and a little explanation as to how the math comes out. Now, filters are a little complicated in that we're going to be delving into a little bit of AC mathematics, and I haven't talked about AC much. I do want to do that in Electronics 101, so if you'll just bear with me with this, I'm going to try to avoid serious math as much as possible. I usually do. So, let's jump into this. I'm going to talk about this two ways. Like I said, one way is with complex mathematics, well, not complex mathematics, but with math. And the second way is hopefully a little more intuitive. So, let's talk about RC filters, and we're going to talk about the two. We're going to talk about low pass. These are obviously passive filters. Low pass, you have the input that's passed to a resistor, and then that goes to a capacitor, and that goes to ground, and then you have your output. Then you have your high pass, where you have your input, except this time it goes to a capacitor first, then a resistor to ground, and then you have your output. Now remember that a high pass will pass a frequency less than or equal to the cutoff frequency, and a high pass will pass any frequency, any frequency greater than the cutoff frequency. So remember the difference. Okay. Let's talk about a wave, specifically a sine wave, because it'll make this a little easier. You have a sine wave, and a sine wave looks like this. Sine wave has two phases, assuming this is a non-biased AC signal, meaning that it spends half the time above the x-axis and half the time below the x-axis. Almost said y-axis there. Okay. The time it takes for it to complete one cycle is the period. And the frequency is 1 over the period. Now, the cutoff frequency cutoff is 1 over 2 pi RC. It is also, if you were to look at this in its angular cutoff frequency, it's 1 over RC. Why do we care about its angular cutoff frequency? Angular frequency is like normal frequency, except you multiply it by 2 pi. This is in radians. Remember that a period of a sine wave, or a sine wave will complete one period, will be on a complete period in 2 pi. So that is the difference between the two. That's to go from radians to hertz. Okay, so why do we care about that? Because of this simple equation, T equals RC. The time it takes for a capacitor to reach 63% fully charged is RC. And the time it takes for a capacitor to discharge is RC. That's where this comes from. It has to do with the amplitude. Remember that a capacitor, which is the important part of the RC, the capacitor is a DC blocking component. It will block a DC signal. This is a DC signal. You can think of each, if I were to break this wave down into 4 phases, each of them is a DC signal. Or 3 phases, rather. Actually, 2 phases, increasing and decreasing, increasing and decreasing. So if you break this down into 2 phases, so why do you break it down into 2 phases? This is the intuitive bit. It's going to block. You have to look at how much voltage it's accruing, like the integral under it, the area beneath the curve. Now, this is the intuitive bit. It's not the mathy bit, but just bear with me. You have to look at the sum of all of the voltages from here. And it's going to block it if the sum of the voltages becomes too high. Now, where the capacitor lies, here or here, is going to change where or how it responds. So, With a low pass, you have the input. There we go. It goes through a resistor first, and then a capacitor. And then it goes to the output. Now, ask yourself, low pass, it blocks anything high. If you have a low frequency, draw that very lovely waveform again. If you have a low frequency, it's not perfect, but oh well. With a low frequency wave, over the course of say an increasing cycle, the area under it, the sum of all the voltages, is rather great. So it's going to fill up this capacitor rather quickly. So the current will no longer be able to flow from input to ground. It will overflow in the capacitor and then go to the output. If you have a high frequency, let's scroll down a bit. If you have a higher frequency, there's a smaller sum of voltages in between its increasing and decreasing cycles. So the higher frequency is able to flow into the capacitor and through ground. It won't overflow the capacitor, and therefore it won't move on to the output. It'll just keep flowing into the capacitor, flow, discharge, flow, discharge, flow, discharge, never being able to reach the output, because the capacitor will technically have a lower resistance than the output. It's going to flow into here rather than flowing into the output. Remember, current's lazy. So that's why a low pass passes a low frequency signal, because a lower frequency will fill up the capacitor and overflow into the output. Now, the high pass filter you have your input, and then you have your capacitor first, and then you've got your resistor. And then you have your output. Okay, so this passes higher frequencies, so it blocks lower frequencies. Remember, lower frequencies will have a greater integral, and will sum more voltages, will have a higher sum of voltages on increasing and decreasing phases. So it's going to fill up the capacitor and not flow. It's going to get stuck here. It's going to flow and then stop. It's going to flow, stop, discharge, flow, stop, discharge, flow, stop, discharge. And it won't actually be able to get to the output. Higher frequency, on the other hand, has a lower sum. So it's able to flow in, keep flowing, before it fills up the capacitor and reach the output. This resistor is what creates flow. But because this has a resistance, and this resistance is greater than the output resistance, it will just flow into the output. So it's able to move straight through. This is a better example of DC blocking. It's blocking sums of voltages that are too great. So it's able to flow in straight to the output, whereas lower frequencies flow in and get stopped. They're blocked. So that's the intuitive way of explaining why filters, or why RC filters work the way they do. Low pass filters work because lower frequencies overflow the capacitor into the output. High pass filters work because higher frequencies are able to move more freely through the capacitor than lower frequencies that will get stuck. That's the intuitive way. Let's talk about it a little more complicated with math. Let's start with a low pass. You've got your low pass filter. This time I'm going to draw it a little differently. You've got your resistor, then you've got your capacitor, and then you've got your outputs. So this is technically ground. So input, output. Okay. This should look a little similar to, say, this. What's this? There was already an On A Breadboard video about it. Right here. This is a voltage divider. You've got R1 and R2. R2. You've got V in, and then you've got V out. What's V out? V out equals V in times R2 over R1 plus R2. So you can do the same thing that you do with a voltage divider with this. You can treat the capacitor as a resistor. Why? Now we're getting into the AC bit. XC equals 1 over 2 pi FC. What is X? X is the reactivity of the capacitor. Reactivity of the capacitor is how quickly the capacitor will respond, will allow current to flow through the device, through itself. That's essentially what reactivity is, and it's again dependent on the frequency you're going to put in and the capacitance. This is an AC concept, and again we'll talk more about this when I do AC math, well, and Electronics 101 on AC. This only exists in AC, so you only have to worry about an AC. But this reactivity is essentially resistance. Now there's something else in AC. It's denoted Z. This is impedance. Impedance is sort of like resistance, but it's also somewhat related to voltage. So as voltage increases, your resistance increases, but your impedance is constant. Again, we'll talk more about it in the AC video. Impedance is of the circuit, and the total impedance of a circuit, specifically this circuit, is going to be the square root of R squared plus X sub C squared. So it's the resistance squared, that looks like a 2. It's resistance squared plus reactivity squared. That is the total impedance. So with that, I'm going to move on to the next page. I'll just copy all of this math. Yeah, that's it. I'm not going to get all of it. That's a little better. Okay. Okay, so now with this math, we can say, oh, where's my pen? There it is. V out equals V in times R2 over R1 plus R2. We can substitute this. V in equals X sub C over square root R squared plus X sub C squared. That's the mathy bit. Now, that should be times. There we go. Where does this start to reduce the amplitude of frequencies? When does V out start to decrease? V out will start to decrease when, remember this is Z. It will start to decrease when X sub C is less than or equal to Z. And that's true, and this is true when R equals X sub C. And that is where the -3 dB comes in. That's the amplitude at which the filter starts to reduce frequency, or starts to reduce the amplitude of unwanted frequencies. That's where that comes from. This is where all the cutoff comes from. This is the mathy bit. This is the complicated bit. Now this formula is for the low pass filter. Obviously, for a high pass filter, you're going to switch some things around, and it just becomes Vn times R over R squared plus X sub C squared. And again, it still holds true. It's when does this start to attenuate or reduce the amplitude of unwanted frequencies? When the resistance is equivalent to the reactivity of the capacitor. So yeah, that's the mathy bit as to why RC filters work the way they do. Personally, I prefer the intuitive block and flow, but you got to do math at some point. So Now that that's done and we've explained how all this works, let's actually look at how a filter behaves with not only sine waves, because sine waves are easy, but other waves, because filters will simply reduce the amplitude of sine waves. It's boring. But other waves, it will do other things. High-pass filters and low-pass filters react differently to different waveforms. So we'll take a look at that as well. Okay, so let's do a little quick math before we start. What have I got? I've got here a potentiometer. This is pin's a little bent. This is a 10K trimming potentiometer, and I have here a 47 nanofarad capacitor, and we're going to use these to create our filters. Got a calculator here. So let's do a little math. I have a 10. Let's start with this. So I've got a 47 nanofarad. That's 47 times 10 to the negative 9th. And then I'm going to multiply that by the resistance, 10,000. Multiply that by 2 pi. And then I'm going to invert that. That should be division. There we go. And so that is the cutoff frequency. So if I set the potentiometer to its max value of 10 kilo ohms, I should see a cutoff frequency of around 340 hertz. So it's going to be good to remember. Now, what are we going to be using to generate our frequencies? It's my old friend. Keep coming. Ooh, thunder. Got a thunderstorm going on outside. My old friend, my AVR digital synthesizer. So we're going to be using him to generate some of the frequency. Well, actually, all the frequencies and waveforms. I just unplugged him. And how are we going to be demonstrating these? What the filter's doing? Well, ladies and gentlemen, I am very proud to announce I finally have an oscilloscope. It's a DSO Nano V3, which I'm very happy I finally got around to buying, so I can do some more stuff with synthesizers. So very pleased to see him. So got my synthesizer broken out, and we're going to connect that to this breadboard. See, on a breadboard. Title doesn't lie. Okay, then on to the breadboard. We're going to start with a low pass filter. So we're going to connect the potentiometer first, then to the middle pin on the potentiometer, the wiper. I'm going to connect that there, and I'm going to connect that to the ground. So it looks, if I zoom in a bit, so it looks something like that. There we go. Zoom back out. Then I'm going to look around for where I put my probes. There they are. I'm going to connect the probes to the legs of the capacitor, like so. And then I'm going to connect the probes to the oscilloscope. I'm going to turn the oscilloscope on. Put the oscilloscope. Where can I put the oscilloscope? I'll put it right here. Wow, it's almost like it was made for it. There we go. Light's gonna get in the way, so I'll just put this back here. Okay, so I'm going to turn the filter all the way. Well, this is a low pass filter, so in order to make sure all the frequencies get through, I'm going to turn it all the way up. And I'm going to make sure that it's. There we go. Okay, so there is a sine wave. There we go. So there's a sine wave. Now this is a low pass filter, so it blocks low frequencies. So if I bring down the pitch, that's a little too low. You can't actually even see that. You can see the amplitude is, there we go, is fairly maxed out. But if I raise the pitch, you can see the amplitude has decreased quite a bit. And as I move down through the frequencies, you can see the amplitude begin to increase until we're finally back to about a max amplitude. Now, if I hold this here. I'm actually going to try and use the little stand. Nah, it's not even going to remotely work. Oop, see if I can just seat it. Come on. Technology. Can't see that. There we go. There we go. Okay, so now what I'm going to do is tweak. Oh, and there it goes. It finally fell. If I tweak the cutoff frequency, as you can see, the arrow on the potentiometer is pointing in a different direction. You can see we now have a higher amplitude. If I turn the potentiometer all the way down, there we go. And now we have a full wave. So that has zero effect. Turn it all the way back up. Have a better filter. Has more of an effect. So that's a low-pass filter on a sine wave. But you already know that what it does. Let's try a different wave. Let's try, say, a triangle wave. You can see that a triangle wave, or here, if I turn the filter all the way back down, there we go. A triangle wave. Why aren't I seeing anything? Turn it back up. I lose connection? What happened? Someone hold my scope. Oh, there we go. That holds the scope at an appropriate level. Why isn't the scope working? Oh, okay, there we go. I just had the cutoff voltage, the cutoff value incorrect, I guess. Nope. Bad connection? What's wrong? We appear to have a slight issue here, ladies and gentlemen. Oh, almost worked. Oh, there we go. The potentiometer just slipped out. Okay, so at a lower potentiometer value, at a smaller effect of the filter, you can see that the triangle is very pointy. It's very much like a triangle. But if I increase this, you can see it becomes softer. And as I increase the frequency, it almost becomes more and more sine wave-like. Now if I play a saw, you can see, again, it makes it... Normally, a saw wave would look something like... That's really high. Normally, a saw wave would look something like that. But as I increase the cutoff, you can see it becomes softer. So what a low-pass filter does to very pointy waves is it rounds it off. And if I... There we go, that's what it does to a different kind of saw wave. It takes the pointy edges and it rounds it. There we go. And what it does to a square wave does that. Look at that. That looks weird. Doesn't even... Looks sort of square wavy, but it's round. It looks like a capacitor charging and discharging. So that's a low-pass filter. Let's switch this up a bit. So excuse me, Mr. Oscilloscope. I'm going to move the potentiometer so that it is now the second component in the circuit. Put that at the wiper. Connect that here. There we go. And now we reattach this to one of the legs, but we attach the ground leg to ground. There we go. Now as I try to make sure that I don't destroy my circuit. There we go. Okay, getting a little ahead of myself. So if we take a, where is it? There we go. Sine wave. You can see, again, rather boring. And if I decrease this, it goes away. I've cut off all of the frequencies. So that's rather small amplitude. But if I increase the amplitude, or if I increase the frequency, again, it passes higher frequencies. The amplitude increases. Let's see if I can increase the Y position a bit. There we go. And again, as I decrease in frequency, the amplitude of the wave decreases as well. So that's a standard high-pass filter with a sine wave. It's boring. Let's try a square wave, a triangle wave. Again, you can see it did to the triangle wave what the low pass did to the square wave. It makes it look almost like an RC discharge. What a high pass will do, instead of the low pass made it sort of rounder, this makes waves kind of sharper. And this is a saw. You can see what it really does to a saw wave. It makes it a lot pointier. A high-pass filter is considered a differentiator, and a low-pass filter is considered an integrator. So that's what it'll do to a saw wave. That's a different saw wave. And to a square wave, you can really see what it does. So yeah. So that's the two kinds of filters and how they affect not only sine waves, but triangles, saws, and square waves. So that is it. So I'm Human Hard Drive. Thanks for watching.